So today we are going to continue with infinite series. The intention is to see a large class of examples of convergent infinite series. So for that we need something called comparison test. So we will start first today's lecture with comparison test. The idea is very simple. The idea is that given a series which converges, how to find another convergent series using this information that the given series is convergent. That means we like to compare. Okay? So the precise statement is this, that suppose Bn is bigger than or equal to 0 and An given. So I have just given two sequences. One is Bn and every term of that sequence Bn is non-negative, and An is a given sequence. Then if mod An is lesser equals to Bn for all n bigger than or equal to some capital N, and summation n from 1 to infinity Bn converges, then summation An n from 1 to infinity also converges. Okay. Now the proof of this is very simple, but before I come to the proof of this, let me introduce one more notion called absolute convergence. So first let me define absolute convergence. This is very simple to understand, that if summation mod An n from 1 to infinity converges, then summation n from 1 to infinity An is called absolutely convergent. Okay. Now the question is, what does absolute convergence has to do with convergence? Well, that is very simple. So I will just put it as a note. It says that absolute convergence implies convergence. How to prove this? That if I have a series which converges absolutely, then it converges. Well, first note one thing, that if I have an infinite series An such that An is always non-negative for all n, then the absolute convergence is same as convergence. There is no difference, because then summation mod An is same as summation An. So the absolute convergence is really a different kind of convergence if the terms of the series are not necessarily non-negative. Nevertheless, it turns out that if a series converges absolutely, that is, it is absolutely convergence, then the series converges. Well, the proof is very simple if we use Cauchy's criteria of convergence. So let us note again what is Cauchy's criteria of convergence. So Cauchy's criteria, in the last lecture we have described it. It just says that summation An converges if and only if given epsilon bigger than 0, there exists capital N such that for all n bigger than or equals to capital N, summation k from n to infinity ak, this mod is less than epsilon. Okay, that means the tail after some stage is small. Now if I use this criteria, then it is easy to see that absolute convergence implies convergence. So this is what we are going to use. So to prove convergence, what I have to do is, given epsilon, I have to find a capital N such that the tail of the infinite series which starts after capital N is less than epsilon. But notice that modulus summation k from n to infinity mod ak, this quantity is always less than or equal to summation k from n to infinity mod ak. Okay. Now I know that this can be made less than epsilon for large n, as this converges, and hence the first quantity is also less than epsilon. Then by Cauchy's criteria it follows that summation an that this converges. Okay, so this is simple. So once again, what does absolute convergence means? It means summation mod an converges. Then using Cauchy's criteria we could prove that if the series is absolutely convergent, then it is convergent. And to prove that, what we have used is just Cauchy's criteria. Okay, fine. Now let us go to the proof of comparison test. So the first one is, it is given that mod an is lesser equal to bn for all n bigger than or equal to some capital N, and suppose that summation bn converges. Okay. So the way we are going to prove it is very simple. Let us say capital Bn equal to summation k from 1 to n bk. So this is nth partial sum. Okay. Now this would then imply that this sequence Bn is Cauchy, as my assumption is summation Bn converges. That means the sequence of partial sums is a Cauchy sequence. This would then imply that modulus of Bm minus Bn goes to 0 as Mn goes to infinity. Now notice that this quantity is nothing but modulus Bn plus 1 up to Bm if m bigger than n. If m is less than n, then the role of m and n are getting interchanged. But then notice that this also implies that mod an plus 1 plus mod am that is less than or equal to this actually is happening because I am assuming all the bm's are non-negative. So the modulus is not actually required. This quantity actually is bn plus 1 up to bm. Okay. Now I know that mod an is lesser equal to bn for large possible n's, right, after a stage capital N. So I can say that this is true for large mn. That means if mn goes to infinity, then modulus of, so this would imply if capital An equal to summation k from 1 to n mod ak, then modulus of an minus am goes to 0 as mn goes to infinity, because this quantity is dominated by, modulus of bn minus bm, which is actually bn minus bm. If I assume m to be bigger than 0, so then it is plus bm minus bn. Okay. Now that quantity goes to 0 because summation bn converges, that means the nth partial sum forms a Cauchy sequence. So modulus of bm minus bn goes to 0, and since modulus of an minus am is dominated by those things, they also go to 0. So this implies that the sequence an is Cauchy. This implies summation n from 1 to infinity modulus an converges. This implies summation n from 1 to infinity an is absolutely convergent by our definition of absolute convergence. But this then by one of our previous observations says that summation n from 1 to infinity an converges. Okay. So what it says is very simple, that if you have two infinite series, so again I will put it as a note, you have two infinite series, one is summation n from 1 to infinity, another is summation bn. Assume bn is non-negative. If compare the terms now, that is why it is called comparison test. Look at modulus of an, if it is lesser equal to bn for all n or after some stage, so we can say eventually, this implies summation an converges if summation bn converges. Okay. So it's very simple to remember that if you have an infinite series whose terms are after some stage less than the terms of a convergent infinite series, then your series also converges. Okay. Now let us come to the proof of part 2. I know that mod an is bigger than or equal to bn and summation does not converge. I want to prove that summation an also does not converge. Suppose on the contrary, if summation n from 1 to infinity mod an converges, then I already know that bn is lesser equals to modulus of an, right, and summation mod an converges. Try to apply part 1. if you have an infinite series whose terms are less than or equal to the terms of an convergent infinite series, then the infinite series converges. So Bn constitutes an infinite series, summation Bn, and each term is less or equals to modulus An, and summation mod An converges. That would imply then by 1 summation Bn n from 1 to infinity, this converges. I am applying 1. But I have already assumed that summation n from 1 to infinity Bn does not converge. That is the given fact. That means then summation mod An cannot converge, because if that converges, that would imply that summation Bn converges, but it is given to me that summation Bn does not converge. So this is a contradiction. This is a contradiction. So this contradiction tells me that it cannot happen that summation mod An converges. So we learned two things, that if I have two infinite series An and Bn given to me, Bn is an infinite series consisting of non-negative terms. If summation Bn converges and modulus of An is less than or equal to Bn, then summation mod An also converges. In fact, it converges absolutely. On the other hand, if I know that modulus of An is bigger than or equal to Bn and summation Bn does not converge, then summation An also cannot converge. Okay? Now we are going to use these states to produce some more examples of convergent infinite series. So first look at this series. Summation n from 1 to infinity 1 by n into n plus 1. Question is whether this infinite series is a convergent infinite series or it is not. So what we do is we try to calculate the partial sums and see what happens. So what is Sn? Sn is summation k from 1 to n 1 by k into k plus 1. This I can write as summation k from 1 to n 1 by k minus 1 by k plus 1. Okay. These are the so-called telescopic sum. So if I open up the summation and write down each and every term, then cancellations take place. What I have left with is 1 minus 1 by n plus 1. Okay. So this goes to 1 as n goes to infinity. This implies that this sequence Sn converges. This implies then by the definition that the series converges. Okay. Now notice that 1 by n plus 1 whole square, if I look at, that is 1 by n plus 1 into n plus 1, which is lesser equal to 1 by n into n plus 1. But I have already noticed that summation n from 1 to infinity 1 by n into n plus 1, that converges. So this implies by comparison test summation n from 1 to infinity 1 by n plus 1 whole square converges. Okay. And this is same as saying certainly that summation n from 1 to infinity 1 by n square converges. Okay. The difference is, in the previous case if I look at the first term here is 1 by 2 square and the first term here is 1. But adding only a term in a convergent infinite series does not change the behavior of the convergence of the infinite series at all that we have observed. So since the previous series converges, that is summation n from 1 to infinity 1 by n plus 1 whole square, so does this series. Notice that summation n from 1 to infinity 1 by n, that does not converge, that we have seen in the previous lecture. But instead of 1 by n, if I have 1 by n square, then it converges. Okay, so then the question arises, if I look at this infinite series, summation n from 1 to infinity 1 by n to the power p, when does this converge? Certain cases are easy to guess, that suppose p equal to 0, then you get the constant terms, that is always 1, and then the terms don't go to 0. So for p equal to 0, the series does not converge. And the same observation will be true if p is less than 0. If p is a negative number, then 1 by n to the power p actually means n to the power minus p, where p is positive. But then n to the power minus p, that is 1 by n to the power p, it does not go to 0 as n goes to infinity. So the series does not converge. And we have already observed that if p equals to 1, the series does not converge. And if p equals to 2, then the series converges. Okay, but what about other values of p? So that is the question we are interested in. That is, what are the precise values of p for which summation n from 1 to infinity 1 by n to the power p converges? Now for this we need another test, and which is very fundamental in the theory of infinite series. Most of the time it will help you. It is called Cauchy's condensation test. Okay, so suppose I have an infinite series an where an is non-negative and they are decreasing, that is an plus 1 is lesser equals to an for all n. Notice that these conditions are modeled after summation 1 by n to the power p. 1 by n to the power p is always non-negative if I am taking natural numbers, and as n increases for a fixed p, 1 by n plus 1 to the power p is always lesser equal to 1 by n to the power p. So we have a sequence of numbers 1 by n to the power p which is decreasing. So we are just putting this condition here. Okay. Then the test says the following. Then summation n from 1 to infinity an converges if and only if, so this is important, summation k from 1 to infinity 2 to the power k, a 2 to the power k converges. Well, in this case I would start from k equal to 0, not that it matters really. Okay, so that means the series I need really to look at is, first I put k equal to 0, then I get a1, then I put k equals to 2, that means plus 4a4, then I have to put k equals to 3, that means 8a8 plus 16a16 and so on. So this is the series I need to look at to understand the convergence of summation an. Now this new series looks much more complicated than the original series given to us. So you might feel, looking at the statement, that this perhaps is making the problem more complicated. But in many cases we will see that because of the 2 to the power k factor thrown in with the term a 2 to the power k actually makes matters easy for us. Well, let us first try to use this result in certain cases and then come to the proof of it. I say that I can use this result to prove the deal with the question which I was posing, what happens to summation 1 by n to the power p. I am going to use this test for that series. So first I am now going to look at, so this is application first. I am going to look at summation n from 1 to infinity 1 by n to the power p. Notice that the terms here are non-negative, that is one thing. Second, this is certainly true that 1 by n plus 1 whole to the power p is less or equal to 1 by n to the power p. That means the terms are decreasing. Now I am going to use Cauchy's condensation test. That means what I need to look at? I need to look at this series now. 2 to the power k, a 2 to the power k, where k varies from 0 to infinity. But I know what is an. An is just 1 by n. So this series is same as summation k from 0 to infinity 2 to the power k times 1 by 2 to the power k whole to the power p, because an equals to 1 by n to the power p. This implies a 2 to the power k is 1 by 2 to the power k whole to the power p. That means this is same as summation k from 0 to infinity 1 by 2 to the power k into p minus 1. Do you see the advantage of using Cauchy's condensation? Because I started with the series summation 1 by n to the power p, but because of the substitution 2 to the power k a 2 to the power k, the problem has reduced to a geometric series. That means summation x to the power n, and that kind of a series we know very easily how to calculate. We have already got our result that summation n from 0 to infinity x to the power n converges if and only if mod x is less than 1. We know that. That is what I am going to use now, because the above series now can actually be written in the form summation k from 0 to infinity 1 by 2 to the power p minus 1 this whole to the power k. And then by the previous observation, this converges if and only if 1 by 2 to the power p minus 1 is strictly less than 1. Now what are those p's for which this is true, that this quantity is strictly less than 1? The answer is very simple, that this implies p minus 1 is strictly bigger than 0. That is, if p is strictly bigger than 1. Notice that if p is equals to 1, then I get 1, but I demand strictly less than 1. So p is strictly bigger than 1. So if p is strictly bigger than 1, then this series, this converges. That means this converges if p is strictly bigger than 1. Then Cauchy's condensation test tells me that summation 1 by n to the power p converges if and only if p is bigger than 1. For all other p's, the series does not converge. Let us look at one more example, that what happens to this infinite series. Summation n from 2 to infinity 1 by n log n. Notice that n log n grows faster than n, so 1 by n log n certainly goes to 0. But we know that going to 0 is not enough to make the infinite series converge. But it is going to 0 faster than n. Does that make it convergent? That is the question. To check whether this convergence or not, if I apply the comparison test, all I get is that 1 by n log n is lesser equals to 1 by n. But summation 1 by n diverges. From that, neither I can say that summation 1 by n log n converges or not, because less than something convergent gives me convergent. But if it is less than some infinite series which does not converge, then I cannot say whether my series converges or not. Okay. So to tackle the problem, what we do is we use Cauchy's condensation test, because the terms here are non-negative, and again at the same time it is decreasing. So Cauchy's condensation test can be applied. So the given series converges if and only if, by Cauchy's condensation test, summation 2 to the power k into a2 to the power k. But what is an here? Here an is 1 by n log n. So a2 to the power k is 1 by 2 to the power k log 2 to the power k. Okay. So k from, we will take k from 2 to infinity, or maybe k from 1 to infinity, that I cannot take k to be equal to 0 here. Okay. Now this then is same as one by k log 2. Log 2 is a constant, so any partial sum of this, if I call it Sn in summation n from 1 to k, let us be careful here. So an is okay. Then from our calculation we can see that this is same as 1 by log 2 summation n from 1 to k 1 by k, sorry, in this case 1 by n. Okay. Now we know that this diverges because this is just partial sums of the infinite series of 1 by n, and hence Sn does not converge. That implies the given series does not converge. This implies the series does not converge. Okay. So it turns out that if I put instead of n summation 1 by n log n, if I just use the Cauchy's condensation test using 2 to the power k a 2 to the power k, it becomes the partial sums becomes exactly like partial sums of summation 1 by n, which we know diverges. Hence this also diverges. That means the given series does not converge because summation 2 to the power k a 2 to the power k does not converge. Well, here time and again I am using the term diverges. It means it's an infinite series which does not converge. Let's just say that an infinite series diverges means it just means that it does not converge. Okay. Now let us look at another example. Summation n from 2 to infinity 1 by n log n whole square. Okay. Here also I can try to use Cauchy's condensation test, and then let us see what happens. I will get summation k from 1 to infinity 2 to the power k, then a 2 to the power k means 1 by 2 to the power k log 2 to the power k whole square. So all you do is instead of an write 2 to the power k times a of 2 to the power k. Instead of n just put 2 to the power k and multiply it by 2 to the power k. That is the series which appears in the Cauchy's condensation test. So here this then is same as summation k from 1 to infinity 1 by k square times log 2 whole square. But log 2 whole square is a constant, so it is just summation of 1 by k square times 1 by log 2 square. But summation 1 by k square converges, that we have seen, because summation 1 by n to the power p converges if p is bigger than 1. Here the case is p equals to 2. So this converges. That means this infinite series, this converges. By Cauchy's condensation test, that would mean that this converges. Okay. So using Cauchy's condensation test or comparison test, there are many series which we can prove that they converge. Now let us go to the proof of Cauchy's condensation test. Okay. So let us recall the statement again, that an non-negative decreasing, then I have to prove that summation an converges if and only if okay. So first let us assume that summation an converges. I have to show that summation 2 to the power k a 2 to the power k converges. That means I have to look at the partial sums and try to show that it converges. Notice here one thing, since I am dealing with a series of non-negative terms, if I look at the partial sums, as the n increases, the terms of the sequences are going bigger and bigger. So if I want that sequence to converge, it is enough if it is bounded. So if I have an infinite series consisting of non-negative terms, to show that the infinite series converges, it is enough to prove that the sequence of partial sums is a bounded sequence. Okay, we will use it, you will see. So first let us look at the partial sum, let us say Tk of the series. This is the kth partial sum of okay, and choose some n which is bigger than 2 to the power k. That I can always do given any k. Given any k, I look at 2 to the power k and I choose a natural number bigger than that. Now, what is Sn? Sn is a1 plus a2 plus so on up to an. Now, since the terms are non-negative, I can certainly say that this is bigger than or equal to a1 plus a2 up to a2 to the power k, because the terms here are non-negative. Now, this I write in the following form: a1 plus a2 plus I club a3 and a4, then I club a5 up to a8, I go on like this. Then the last clubbing is a2 to the power k minus 1 plus 1 up to a2 to the power k. I can certainly count that how many terms are there in each club. For example, in the first club there are 2, in the second club there are 4, that means 2 square element, and in the last there are 2 to the power k many elements. Now I say that this is bigger than or equal to, let us write a1 plus a2, then I had a3 plus a4, but a3 is bigger than or equal to a4 because it is decreasing. So this is, I can write twice a4, then I can write 4 a8. It goes on like that. I finally get okay, this is bigger than or equal to half a1 plus a2 plus twice a4 plus 4a8 plus 2 to the power k minus 1 a2 to the power k, which is precisely, if I take half common, it's half of a1 plus 2a2 plus 2 square a2 square plus 2 cube a2 cube and so on up to a2 to the power k, which is nothing but half tk. This then would imply that tk is less or equal to 2 times Sn. Now, since ans are non-negative and I have assumed that summation an converges, that implies that the sequence of partial sums Sn, that is a bounded sequence. That means the sequence 2Sn is also a bounded sequence. This implies that Tk is a bounded sequence. And since summation 2 to the power k a2 to the power k is also a series of non-negative terms, once I show that its partial sums forms a bounded sequence, the series converges. But I have shown that the sequence Tk is a bounded sequence. This implies so we got the result in one direction, that if summation an converges, then summation 2 to the power k a2 to the power k also converges. Now it is the other way, that suppose summation over k 2 to the power k a2 to the power k converges. Assume that I have to show that summation an converges. That means I just have to show that the sequence of partial sums Sn of summation an that converges. That is a bounded sequence. That is good enough. Okay. So what we do is, for fixed n, choose k such that n is less or equals to 2 to the power k. Okay, and then start with Sn, that is a1 plus a2 plus a3 up to an. Okay, then I write this at that this is less or equals to a1 plus a2 plus a3 plus a4 and so on. Okay. Since 2 to the power k is bigger than n, I am taking many more terms, and since every term is non-negative here, certainly right hand side is much bigger. Okay. Now this I further write as that this is less than or equal to a1 plus, now a3 is lesser equals to a2, so it is lesser equal to twice a2 plus, then I get it is lesser equal to 4a4 and so on. For example, the last term which I have written here, it turns out to be 2 to the power k, a2 to the power k, which is precisely tk. Okay. Now since I have assumed that 2 to the power k, a2 to the power k converges, and it is a series of non-negative terms, that implies that Sn is bounded as the sequence tk is bounded. As I said, if I have an infinite series consisting of non-negative terms, then for it to converge, it is necessary as well as sufficient that its sequence of partial sums is a bounded sequence. Now since summation 2 to the power k, a2 to the power k converges by my assumption, that means tk is a bounded sequence. But since every term of Sn is lesser equal to some tk and tk is a bounded sequence, that implies the sequence Sn is bounded. This implies, since this is an increasing sequence of non-negative terms, that means the sequence Sn converges. This implies summation an converges. So this completes the proof of Cauchy condensation test. Now in the next lecture we will continue with infinite series. We will talk about some more tests which will be needed in many practical situations where you are dealing with some infinite series. Those are called limit comparison test or ratio test, things like that. That we will continue in the next lecture, and then see some more examples of convergent infinite series. So in this lecture we have essentially concentrated only on two tests which will give you examples of convergent infinite series. One is the comparison test, the very fundamental one. You will see that when we go to ratio test, we will again use in some form or the other the comparison test. Then we have understood the nature of a very fundamental infinite series given by summation 1 by n to the power p. You will see that this is one of the fundamental infinite series, because most of the time when you deal with some infinite series to test its convergence, what you actually do is you compare those infinite series with the series summation 1 by n to the power p, whose behavior now we know very well. And the third one is Cauchy's condensation test. That is another very fundamental test for convergence of an infinite series. This test actually have produced the convergence results of summation 1 by n to the power p. So this is for today. In the next lecture we will continue with infinite series again.